Thank you so much for the invitation. And today's topic appears to be quite intimately related to many different things. And the plan of this talk is quite ambitious, as you can see. We have 6 sections that we would like to cover today. The first 2 will be covered by Vladimir Vinogradov, my friend and co-author. He'll be talking about history of Lambert function and Lambert equation. After that, it will be the main motivation of the problem that we consider, which is related to solution of the generalized Lambert equations, which looks like that. And it will be sitting here all the time. I'm not going to erase this part. So after that, we'll be talking about generalized Lambert function. We'll give formal definition and discuss certain properties of this generalized Lambert function. In particular, we will find asymptotic at 0 and infinity of the solution to this equation. We compare different approximations, and the most interesting part to me is probabilistic nature of the generalized Lambert function, which appear to be connected to Riemann zeta function and so-called Turnheim double series, very elegant area of mathematics, which I didn't know until I started working on this project. So having said that, I will give the floor to my colleague and co-author, Vladimir Vinogradov, and he is going to describe the first 2 sections of this talk.
Thank you, Alex. The frame is green now, so it's my turn. So first of all, this is the function that first emerged in the second half of 18th century in the correspondence between Leonhard Euler and Lambert. So actually, Euler did a lot, but when it came to the time to name this function, so people realized that so much was named after Euler, so Lambert was an obvious choice to name this function. So when you consider an equation y equals x times e to x, so you want to find the inverse function. So you want to express x in terms of y. I understand that this equation, which is quite natural, is also written on chalkboard. And so you get an equation which was a hot topic starting from 18th century. And this solution to this equation, which is a multi-valued function, was really, it wasn't named until the year 1996, when a famous paper by numerous co-authors, including Donald Knuth, and some of my colleagues and friends from University of Western Ontario, namely Rob Carlos and David Jeffrey, was named. So in the year 2016, when we celebrated 20 years of formal naming this function, there were already 4,000 quotes of that paper, including 2 of my own, and I was asked to speak on applications of this function in probability and statistics during that meeting at University of Western Ontario. So, and this function emerged. Alex, can you please move to applications after 1990 slide. So, this function emerged in population dynamics, biochemistry, disease dynamics, and it's not that hard to figure out that solving equation e to negative cx equal to a times x minus b can be expressed in terms of this function. And I ought to warn you that this function has two real-valued solutions. One of them is called principal real branch of the Lambert function, and the other one is called lower real branch. There is a world-famous poster produced by several co-authors of that famous 1996 paper, which is available online. So, and then specialists in quantum mechanics often incurred a more complicated equation, which is shown in red on the bottom of the current slide, namely e to negative cx equals the ratio of two polynomials of the degrees n and m, Pn of x over Qm of x. And I also should mention other areas of applications, such as atomic, molecular, and optical physics. So it's about time to start speaking of applications of this function in the theory of branching processes. And it will be my next topics, but I also should mention that the principal real branch of this function, denoted by W sub P of x, where P is for positive, admits a representation as a convergent series at zero, and so it's a representation for which the radius of convergence is the reciprocal of E. And also this function admits a continued exponential representation, namely W of x equals x times e to negative x times e to negative x times e to negative x, etc. So the latter representation is actually going to be very important for today's presentation. And Alex, can you please show the slide? Yeah, so this is the slide for Galton-Watson process. And in fact, this is a topic that I brought up in the second half of my Toronto probability seminar on September 30, 2019, which Balint chaired. So we consider Galton-Watson process that starts from one particle with the particle production generating function pi sub nu of z equal to the infinite sum over n from 0 to infinity of probability that nu equals n times z to the power n, where random number nu is the number of descendants in the first generation. So of course we know that in order to find the probability of extinction of such Galton-Watson process, we need to solve equation that pi nu of z equals z, and look for the least root of this equation that belongs to the interval from 0 to 1. Yes, so and a problem that was solved, so it's given in Jager's book on applications of branching processes in biology. So in the case where the number of descendants of a founding father nu has Poisson distribution per se with parameter lambda, then in the we need to solve the equation e to lambda times z minus 1 equals z. So, and in the supercritical case for which lambda is greater than 1, we can express solutions in terms of the Lambert W function. It will be actually negative lambda to negative 1 times W sub p of negative lambda over e to lambda. So it's not that hard to find it in the closed form. However, there are other interesting distributions which are proposed to consider, and an important distribution is the so-called discrete stable distribution with parameter alpha that is presented on the bottom of the current slide. So for which the probability generating function or its particle production generating function in the context of branching processes is equal to e to the power negative lambda times 1 minus z to the power alpha, where alpha is between 0 and 1. So when alpha is 1, we clearly obtain the Poisson distribution with mean lambda. So for alpha less than 1, the average is going to be infinite, and we get the so-called supercritical explosive Galton-Watson processes. And I want to say a few words about discrete stable distributions. So they have an interesting common property with Poisson distribution. Namely, if we consider the discrete stable sum of ID Bernoulli trials, that then such a discrete stable random sum of Bernoulli trials is also discrete stable, but with different parameters. So when we consider such Galton-Watson process with branching mechanism given by discrete stable distribution with alpha less than 1, we can replace parameter alpha by parameter beta, which is its reciprocal. Beta is 1 over alpha, and it's greater than or equal to 1. Lambda is any positive real, and eventually we will need to solve the following equation: e to negative lambda x equal to 1 minus x to the power beta. And here x is between 0 and 1. So it's this is the equation we need to solve in order to find the closed form representation for the probability of extinction of such Galton-Watson process. Yeah, and Alec, yeah. So
Okay.
I should say that solution to this equation does exist. So if you consider equation 1, where script f of x is e to negative lambda x minus 1 plus x to the power beta equal to 0, with beta greater than 1. So it's straightforward calculus to show that this equation has a root on the open interval between 0 and 1, which is going to be the probability of extinction. And the question is how to find it in closed form. So, and you can see a toy example that shows the graph that gives you extinction probability. In the case where beta is slightly greater than 1, it's 1.11. Thank you. And Alex, I understand that you will take over now, yeah?
Yes. Yes, I plan to take over now, and we'll continue with other sections of our presentation.
Thank you, Alex. And I will be available for questions.
Okay.
Sure. Thank you.
So in order to define generalized Lambert function related to equation for the extinction probability, we need to notice one simple thing and very useful thing, that generalized Lambert equation written here defines implicit function, but inverse function to y can be expressed in terms of elementary function, which is very important comment here. So we take a function that is equal to minus log of 1 minus y to the power beta divided by y for y between 0 and 1, 0 when y is equal to 0. Parameter beta will be always related to stability parameter by this long-standing relation for the rest of our talk. And now, once we define the function x beta, we can define inverse function, and it is called generalized Lambert. So it's one-to-one correspondence. It is not difficult to notice nice properties of the function x beta and corresponding properties of y beta, namely monotonicity, the values at 0, the values of infinity. And this allows us to construct so-called benchmark approximation of the function. What we can do is we have a grid of the unit interval. If you take an arbitrary grid, then using the definition of the inverse function, you can find corresponding values of x. And this construction of the inverse function allows us to compute precisely the values at arbitrary point.
Question.
Sure.
Why is the Lambert function special case of the generalized Lambert?
If you substitute,
Excuse me, may I please ask to use the microphone? So if you ask a question, please use portable microphone.
okay. So the question was,
So why is the Lambert function a special case of the generalized Lambert function? How can we see that?
if we substitute beta equals 1, then we'll notice that after linear change of variable, we obtain Lambert, classical Lambert. And it is related to the function w. Yeah, because it will be 1 minus y is equal to exponential of minus xy. And then you can write this as exponential of minus x, 1 minus y. X times 1 minus 1, exponential of minus x. And then you link it to classical Lambert.
Thank you.
Okay. So we construct benchmark approximation using this idea of inverse function and plot this function for different values of beta for x between 0 and 7. So this is how it looks like. For some values of beta, it has 0 derivative at the origin. For some values, it has infinite derivative. But it's just a comment. It's not important now. Beta is always greater or equal than 1 in this. So as you remember, in the second or the third slide, we demonstrated very nice continued exponential for the classical Lambert W of x. So similar continued exponential representation can be derived for generalized Lambert. Namely, what you have to take is you take the function 1 minus exponential of minus x, and then you raise it to the power alpha, multiply by x, take exponential again, subtract from 1, and you continue doing that. You obtain continued exponential for generalized Lambert. And naturally, this function should be understood as iteration process, and we can prove that no matter how we choose x, how we choose positive x, we always have the limit in this iteration scheme. And in what follows, we'll demonstrate that it is actually not important to start from 1. You can start at arbitrary point between 0 and 1. So given positive x, the fixed point of this mapping is a non-trivial solution of the transcendental equation that we call generalized Lambert equation. And the iteration process here is a rather fast algorithm for computation of the values of our function y. The iteration process is illustrated in the slide. Here we have two lines, red and blue. And on horizontal axis, we show the number of iterations that is required to converge to the limit. So our mapping that we use for iterations is this one. And remind you that alpha is always 1 over beta, or beta is always 1 over alpha. We start from the red line corresponds to iterations that start from 1. Blue line, blue convergence corresponds to iterations that start from the values that are close to 0. And as you can see, we have convergence of two lines, and this convergence is monotonic. More precisely, we have here conditional monotonicity of the iteration process, because if we start above fixed point, then we go down and always converge monotonically. If we start below, then we go up. It's very natural and rather simple. What we noticed that depending on how we close to 0 or to infinity, this convergence is not very fast. So in the middle, you converge in, say, 7, 8 iterations, and the problem is done. But when you are close to 0, then the number of iterations required to reach certain level of accuracy can be rather large. So it can be 40, 50, which is not probably very good. But anyways, it works nicely and it is fast. And it was the main reason why we started looking at asymptotic expansion for the Lambert, generalized Lambert function. And we figure out that one simple asymptotic expansion that can be easily obtained from this generalized Lambert equation has this form. And notice that in this expansion, the degrees of the argument are not integers. So they are 1 over beta minus 1. And it is very natural for this problem to have asymptotic of this kind. So this is very simple asymptotic. In order to get it, we just use trivial comment that exponential function when x is small is approximately 1 minus xy plus 1/2 of xy squared plus little o. And you substitute it into this generalized Lambert equation, do cancellation. After that, you derive this asymptotic formula. which is very nice, but the next question is maybe it's possible to improve this trivial asymptotics, and indeed it is possible. And our friend and colleague Andrey Marchenko, with some effort, derived better asymptotic relation that is represented by this lemma. So what you have to do, you have to take the series that is shown here, only 4 coefficients, and compute expansion shown in the slide. So, and jumping a little bit ahead of the train, I have to say that this asymptotic works much better, and it is very easy to compute, and it shows the structure of asymptotic expansion, how these degrees of x should be taken in order to get nice approximation. The next interesting observation is that you can derive very simple lower and upper bounds for the function y beta. And it appears to be that what you have to do, you have to take 1 minus exponential of x and raise it to certain powers, 1 over beta, which is alpha, and 1 over beta minus 1. And if you do that, you obtain the following picture. So by red line, we show here benchmark approximation, which is true value of the generalized Lambert function. By blue line, we show here lower bound. And by dashed line, dashed magenta, I guess it is upper bound. And the function behaves as follows. So when x is close to 0, it is practically it practically coincides with the lower bound, but when x is large, it is very close to the upper bound. So that's what we know about this generalized Lambert function and these bounds. And one natural question is, maybe it's possible to use lower bound as asymptotic at 0. And the answer is actually it's not good asymptotic. It's not very natural. We'll see it in the slide. But let's go down to let's go back to the iteration process that can be used for solving this equation. It is written in terms of original parameters of Galton-Watson process. And what's important to notice that when you build a graph of the function f beta, you observe that when beta gets close to 1, then this point, the minimal value of the function, gets closer and closer to 0. And this represents certain computational problem for the numerical methods, because numerical methods that are based on bisection idea just cannot find the initial interval where you have to find the root. So it's difficult for them. And it's not that just beta should be extremely close. When we take beta less than 1.1, we ran into this numerical difficulty. And basically, it was one of the reasons why we started looking at asymptotic expansions. Now, the next observation is that the function f beta that we plot here, it has negative derivative at 0. Then at x equal to 1, it should be equal to positive number always. It should be equal to 1 minus exponential of minus lambda. The right-hand side, the left-hand side is 1. So naturally, because the function itself is monotonic after this, the vertex of this so-called parabola, when x is greater than the vertex of the parabola, then our function is monotonically increasing. Naturally, there must be root of the equation that we are looking for. But if we cannot find the initial interval, then we have a problem, and that's why we started looking at asymptotic approximation. And the second asymptotic approximation, this one, works better than the first one, and this is demonstrated in this slide. So if we compute the distance between benchmark and asymptotics, represented by green line, which corresponds to the simple asymptotic expansion approximation 1, and the red is more precise four-term asymptotic approximation, then you will see that log distance is much better in the case, and log distance is the distance between two curves that we compute using benchmark approximation and asymptotic approximation. And the blue line corresponds to lower bound, and it's the worst case. So lower bound is not a good approximation. Now the question is, how do we compare iterative processes, and how does the rate of convergence depends on the choice of initial value? We can choose y1 equal to 1, we can choose y1 close to 0, and naturally the number of iterations depends on the choice of y1. So in order to compare different strategies, we need to introduce the number of iterations, required number of iterations, that is naturally defined as the minimal value of parameter n when the distance between the iterated solution yn and benchmark is less than or equal epsilon. Epsilon is here some positive number. And the next slide will illustrate the situation for three different strategies. The first strategy corresponds to initial approximation y1 taken from the low boundary, upper boundary, and middle point. So you take somewhere in between. And what's happening in this case? The situation is as follows. When initial approximation is close to 0, then the lower bound works better. So the number of iterations required to reach epsilon level of accuracy is the best when you take the lower bound. When you move away from 0, midpoint approximation appears to be much better than the other two. And when y is close to 1, so in the right tail of the distribution, we have upper bound dominating the other two. That's what's happening. And it is quite natural in this situation. So we sort of expected this type of result. Another interesting thing is related to this area. I suspect what's happening here is that the choice of y1 appeared to be very close to the true solution of the generalized Lambert equation. That's why the number of iterations appear to be less than 10 in this case. But naturally, the choice was sort of random with respect to true or benchmark approximation. So after that, we decided to explore probabilistic aspect of the generalized Lambert function, and we figure out that all solutions to generalized Lambert equation represents certain cumulative distribution function. And it is natural to introduce a random variable that has this distribution. So formally speaking, we proved here three things. We first proved that at zero, our solution tends to zero. At infinity, we have 1. And we have monotonic functions. So the first derivative of y beta is greater than 0. Once you prove these three things, you immediately obtain that the set or the class of functions y beta, which represents solutions to generalized Lambert equation, belongs to is a subset of D plus, and this stands for cumulative distribution functions of the non-negative random variables. But what we have to note is that the function y beta is not known to us in closed form, but we have closed form representation of the inverse function. And because of that, we can conclude that we immediately apply Monte Carlo algorithm for generation of these random variables. Because as you surely know, if you know the CDF of a random variable, then applying inverse function to the uniformly distributed random variable, we obtain samples of the random variable that has this cumulative distribution function. So this idea helps us not only to generate Monte Carlo scenarios, but also to find the moments of this random variable. And here, the most interesting thing starts. So we give the following definition. We say that the random variable xi beta has the generalized Lambert distribution if CDF of this random variable is y beta, which is solution to this generalized Lambert equation. I'm not sure about this name. We just came up with this idea. Maybe it's not the best terminology, but for now, let's keep it simple and call xi beta generalized Lambert random variable. So once we give this definition and using the fact that inverse function is known to us, we find closed form representation for the moments of this random variable. They appear to be represented by this integral. And this function appears to be related to, as I promised in the very beginning of our talk, it appears to be connected to Riemann zeta function. It appears to be connected to Sondheim double series. And there is a connection that I do not understand because I'm not specialist in modern field theory in physics in general. And there is a connection to so-called Witten zeta function. So, but really, I can't say much about this connection. So let's look a little bit at the moment. So the first thing is that you can transform the previous expression to this one. And this allows us to find closed form solution for the moments. Mn, capital Mn, in this case for n equals 1, 2, and so on, is the value of nth moment of the random variable xi beta. Naturally, it is useful to look at the rate of growth of these moments, and this is pretty fast. What this graph illustrates is dependency of the log moment, log of nth moment as a function of n. And for small n, like n equals 1 and 2, you obtain numbers that are pretty small, but when n increases, you quickly run to infinity, so it's very fast. One nice thing that immediately points at connection to Riemann's zeta function is that if you compute the first moment, you can compute it using this fact that you take the tail of the distribution function 1 minus CDF, integrate it from 0 to infinity, and you obtain the first moment, and it is equal to pi square over 6 multiplied by alpha. 1 over beta, remind you, is equal to alpha. So one nice fact. And the next thing to look at is to understand what's happening to other moments. Maybe there is also very nice relation to Riemann or some other popular constants. What we figure out that when we compute standard deviation as a function of alpha, naturally, it is not linear function. It has actually maxima, and then it goes a little bit down when alpha is between 0 and 1. And it's worth to look at this nonlinearity effect and understand what kind of analytical description we can give to the function sigma, which is standard deviation of the random variable xi beta. And we also looked at one aspect of this probabilistic connection, namely, Vladimir asked me the following question: is it true that the probability measure corresponding to generalized Lambert equation is determinate? Determinate means that probability measure is defined by its moment. So if we specify the sequence Mn, the question is it true that there is unique probability measure that corresponds to the sequence of moments? And the answer appeared to be positive. So this sequence of moments uniquely defined probability measure, but I am not going to talk about it because we are pretty much exhausted our time. So let me talk a little bit about connection to Riemann and harmonic Enternheim harmonic series. So the second moment, as we noticed, can be expressed in terms of this integral. And then it is not very difficult to derive the following nice representation as a double series. This type of double series is called in mathematics Enternheim double series. So we have summation 1 over k, 1 over m, 1 over k plus m. But here we have to subtract the argument x, which is between 0 and 1. So the series obviously converge. And it has many interesting connections. First of all, if we represent this term as a sum of geometric progression, this denominator x divided by k plus m, we come up with the constants that have this type of structure. We denote them by AL. That's what we will have. And the constants AL appear to be related to harmonic series, which is the sum of from 1 to n of the reciprocal of 1 over k. So Hn is given by this relation as always. And the nice thing is that our integral appears to be generating function for the sequence AL. And this analytical connection allows you to find a lot about the coefficients AL, lots of identities that people working in the area of Enternheim double series are familiar with. And that's what we discovered in the end that there is a representation of the coefficients AL that are related to the moments of our random variable xi beta can be expressed in terms of harmonic series and zeta function shown here. Zeta here is Riemann zeta function. In particular, one can find the value of the coefficient A0, which is 2 times zeta of 3. And that allows us to find a representation of the variance of the random variable. When alpha is close to 0, the linear term is equal to coefficient A naught multiplied by alpha. Now, all this information is obtained from analysis of the second moment. There are many more. And what's interesting is that if you start analyzing relation between nth moment of the random variable xi beta and series, corresponding series that represent our integral, will have many more challenging and interesting relations. And this aspect is not well understood yet. It is just, we can say, work in progress, but maybe it's even for some future generations of young people that might be interested in understanding this connection between generalized Lambert, Riemann, Thornheim double series, and maybe many other things. So, and here I think I will stop and mention that our preprint can be found on arXiv or my ResearchGate paper page, and there are a few important papers by Lambert, Johann Heinrich Lambert himself, Leonhard Euler, and some important applications connected to classical Lambert W function. So this paper is very important. It was published in 1996. There is also a monograph dedicated to Lambert W function. And so it looks to me a very challenging and interesting area that establish connection between theory of transcendental equation and probability. So and here I would like to stop.
Are there any further questions?
Please use the microphone if you ask a question.
Are there any further questions?
Can you hear me?
Yes, but if someone else is asking question, please give them a portable mic.
Can
Valid.
you hear me, Vova?
Yeah. Thank you.
Yeah? You sure?
Yeah.
Okay. So the question is, so you have this generalized Lambert CDF, right? Have you found this in any applications? Does it arise in some probability problems in any way that
Not
you
yet.
know?
Not yet.
Well, it's just a function that it's
Yeah,
monotone.
so-
And, yes.
You see, when you do such thing, it is natural to look at the object from probabilistic point of view. And when you notice that y beta actually represents cumulative distribution function, so the next natural question is to find what kind of properties does this random variable have, right?
Okay. Any other questions?
Yeah, if I can adapt to Alex's answer. Yeah.
Yeah.
So, but from the point of view of distribution theory, it's an interesting class of probability distributions having interesting asymptotics. So such a class is interesting in its own right. And perhaps it could be used for modeling extremal events, etc. But these results are very new. They were derived as early as the just past spring. Like I'm speaking about March of this year. That's where these results emerged. And if I may also comment on this paper by Carlos Gonnet, Herr Jeffrey, and Donald Knuth. So Donald Knuth contribution and applications in theoretical computer science was in terms of the tree function, which is important in computer science, which is just a very slight modification of the Lambert W function.
Okay, thank you.
Come on.
Anything else?
More questions, please.
Okay, so if there are no further questions, then let's thank our speakers again. Thank you both.
Thank you.
Thank you. Thank you for coming.